Right, ladies and gentlemen, good afternoon. We will continue with chapter 4 on transient heat conduction. Yesterday, just as an introductory lecture, we've looked at where does transient heat transfer or unsteady heat transfer fits into the bigger picture of heat transfer. And I've explained to you that transient heat transfer is about the specific study where we are interested in how the temperature changes as a function of time. And there's a large number of applications in industry and also in society where we are exposed to this type of problem on a daily basis. Then we've continued with deriving the equation, which is this one here on the board, from first principles, from an arbitrary body with a certain volume, a certain surface area and a CP value in a certain environment. Right. So we've ended the lecture with this period. And I've told you we're going to come back to this B because it's a very important thing that we need to understand exactly what that term actually means. Now to do that, I'm going to do two examples. Okay. Two examples, and then, only then, I'm going to come back to that term and give you another perspective in terms of specifically when that equation is valid and can be used and when not. Right, so the examples, the first one is an example of a sphere. A sphere, and it's made from silver, and it has a diameter of 10 millimeters, like a ball bearing. Okay, 10 millimeter ball bearing sphere, and its initial temperature is 150 degrees Celsius. Maybe it was in an oven or something like that. And then it is taken out of that environment at T equals 0, and the environment temperature now changes to an environment where the temperature is 20 degrees Celsius and the heat transfer coefficient is equal to 12 watts per square meter degree Celsius. So we can immediately see that the heat transfer is going to be from the high temperature to the low temperature, and there's going to be a heat transfer. Okay. In the beginning, the temperature difference is going to be 130 degrees Celsius because this sphere is going to be at 150, that is 20, so it's going to be 130. But then as it cools down, the delta T decreases as function of time. Okay, so this heat transfer rate will not be a constant. It will also be a function of time. Okay. Right, now to consider this problem, the question that is being asked to us is, how long will it take? What would be the time for this sphere to cool down to a temperature of 50 degrees Celsius? Okay, so how long will it take before the temperature of that sphere is 50 degrees Celsius? Right, now if we look at this equation, we see that we need certain things. We need, for example, the CP of the sphere. We need the density, and the surface area we can work out, the heat transfer coefficient we have. So we need that. Where do we get it? Well, that is one of the reasons why you should know your textbook very, very well. All of you passed thermodynamics, and you know how important that tables is. And you know it is important that you put in hours to work with those tables. So at the back of your textbook of Cengel and Ghajar, you also have tables. Okay, and we're going to use them a lot, especially in the tests and the exams. So one of you asked me yesterday if you should bring your textbook every day. I would recommend that because in class I'm going to refer to it a lot. It will give you an opportunity to go and look for it. And many of you, by the time that you're going to write test or exam, is going to put in stickers on the side telling you and showing you how you can get to those tables very quickly. So this table specifically, oh, and this sphere is made of silver. Sorry, I haven't mentioned that. So it's made from silver. So if you go and look in the textbook, typically in table A3, then the properties of silver are given there. So that is where it came from. And The K value is equal to 429 watts per meter Kelvin. Okay. The density of the silver is 10,500 kilograms per cubic meters. And the CP value is equal to 0.235 kilojoules per kilogram Kelvin. Okay. So that's the properties. You're going to get it out of your textbook. And properties in this course is actually very important. In many cases, you will have to go and get properties. You will have to go and get certain values, and most of them are available in the tables at the back of the textbook. So, if we now look at this problem of the temperature as function of time, then it starts with the temperature which is at 150 degrees Celsius. So there's the initial temperature. Okay? And in the limit, after a long time, this temperature can only decrease to a temperature of 20 degrees Celsius. Do you get it? It cannot go lower than 20 degrees Celsius. So that is the limit of 20 degrees. And in many cases, these simple things are very, very important for us to write down and to make a sketch of, and I would recommend it to you. Because when you start doing number crunching, you can go and get any value, and you write it down. But that is where, in many cases, you will have to think about your answer. So the first thing that we know here is that any answer between those two limits will not be correct. You get it? It's very simple, but it is always important that we go through this exercise and that we take note of that. So let's suppose that is T equals 0, then we know that that silver sphere was at a temperature of 150, and now the question is, to a temperature of 50, somewhere there, how long will it take before the temperature of the sphere decreases to 50 degrees Celsius? Now, if we look at that equation, it's a very simple equation, so we just need to do the number crunching. So let's start with B. We do have the heat transfer coefficient, but we need the surface area. We've got the density. We just need to calculate the volume of the sphere, and we've got CP. And then we've got B. Okay? The temperatures, all the temperatures we have, and then we can calculate the time. So it's a very simple and easy problem. So let's start with calculation of the surface area. The surface area of the sphere is equal to pi multiplied by d squared. Okay. Pi multiplied by 0.010 squared, and that gives us a surface area of 3.142 multiplied by 10 to the minus 4 square meters. You agree with that? Right. So that is the surface area on the outside. Now we need the volume of the sphere. Volume of the sphere is equal to pi divided by 6 d to the third. So it is pi divided by 6. The diameter is 0.010 to the third, and the volume is therefore equal to 5.236 multiplied by 10 to the minus 7 cubic meters. Okay. So let's go and calculate the B value. The B is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume, and CP. Ladies and gentlemen, am I going too fast? Not? You're fine? Okay. So the heat transfer coefficient is equal to 12. Okay. The surface area we've determined just now, it is 3.142 multiplied by 10 to the minus 4 divided by the density. Here is the density, 10,500 multiplied by the volume. Here's the volume, 5.236 multiplied by 10 to the minus 7, and multiplied by CP, and CP is equal to 0.235. Are you all happy with that? No! What's wrong? Yes, thanks. Just want to make sure you're all awake. 0.235 multiplied by 10 to the 3. One of the very simple things that in many cases go through in our calculations, and it has a huge effect. So be careful for that. So the B value is then equal to 2.918 multiplied by 10 to the minus 3, and the units is actually per second. Okay, so now we are ready to do the substitution in our equation. The equation that we've derived yesterday for a lump system is equal to the temperature at any specific time minus T infinite divided by Ti minus T infinite is equal to E to the minus BT. Okay. The temperature that we want. Okay, I'm first just going to write this equation like that because we're going to use it later on. So let's just write it like that. The environment temperature is 20 degree divided by the initial temperature is 150 minus the environment temperature again is 20 is equal to E to the minus B, and that is 2.918 multiplied by 10 to the minus 3T. Okay, and I want to use this, name this equation, equation 1, because I'm going to come back later to it. So it's just in that general format. Okay, so the only thing that we now need to do is, we want to know when will the temperature be 50 degrees Celsius. So it's very easy. So it is 50 minus 20 divided by 150 minus 20 is equal to E to the minus 2.918 multiplied by 10 to the minus 3T. And if we solve the T, then the T is equal to 502.5 seconds, and that is 8.38 minutes. Okay, so it will take 8.3 minutes for this silver sphere, typically a ball bearing made from silver that was at a temperature at 150 degrees Celsius to cool down to 50 degrees Celsius. So if we now put in the graph there, then we know that is about 8.4 minutes on the graph. Okay. Are you all happy with that? Any questions? Anything that you do not follow? Nothing. Okay. So what I want to add now to this problem is now, let's come back to equation 1. Okay, that is why I've written it in that general format. Now we can go and solve T also for different times. Okay, for different T's. So let's suppose we want to know what is the temperature of after 1 second. So 1 second after we've taken out that sphere, what would the temperature be? Anybody like to take a guess? Nobody? You're not brave enough yet, Sinak, I see. Okay, so then the temperature would be 149.6 degrees Celsius. So 0.4 degrees Celsius drop already after the first second. After 10 seconds, the temperature would be equal to 146.3. So about 4 degrees Celsius drop already in 10 seconds. In 60 seconds, it would be 129.1. Okay. And in 120 seconds, it's 2 minutes, then it would already be 111.6. So if we come back to the graph and we look approximately for 2 minutes, that temperature there would be 111.6. Okay, now I did put actually this equation into my ease program for these calculations, and then I wanted to check how long will it take for the temperature to drop to 20 degrees Celsius. Okay, any guesses? How long will it take to drop totally to 20 degrees Celsius? Okay. Now theoretically it should never be, because this line actually would never get to this line. But with a computer with 64 digits, there is a limit, and my calculation showed it would be 4,830 seconds, and that would be 80.5 minutes. So after about 80 to 81 minutes, the temperature of that sphere would be 20 degrees Celsius. Any questions? Nothing? Good. Right, the next problem, the second one, is one that many of you can relate to very well. That would be a can of beer. Okay? Can of beer. It has a diameter of 60 millimeters and a height of 125 millimeters. Okay. Now the first year student forgot it in the boot of his car. Okay, it's standing in the sun. And the temperature of the beer is 40 degrees Celsius. Okay. Now I don't know about you, but I don't like beer at that temperature. I like my beer at 10 degrees Celsius. Okay. So you will get to that just now, but let's look at this beer. It is in a can, aluminium can, but the resistance, the thermal conductivity of the aluminium is very high in comparison with what is inside the beer. And beer, 80 to 90% of it is water. So we are going to make the assumption that this is actually water. If you go and look in your textbook and you look for beer, I don't think you're going to get it in the tables. So in many cases, you have to make these types of discretionary assumptions that we as engineers have to make. So we're going to assume it's water. And at 40 degrees Celsius, the density of the water is 1,000. The K value is equal to 0.631. And the CP value, in this case, I'm not going to write it as kilojoules, I'm going to write it as 4179, and I'm not adding the units here because I'm a little bit out of space. Okay, but the units for density, of course, kilograms per cubic meters. For K, it is 0.631 watts per meter Kelvin, and the CP value is 4179 joules per kilogram Kelvin. Right. So what we have here is, okay, so we want to know the problem. Okay, the beer is warm and the rugby is going to start, and we want to know how long is it going to take to get this beer to 10 degrees Celsius, and what are our options. Okay. So the problem is, how long is it going to take to get this beer to 10 degrees Celsius? Okay. Now one option would of course be to put it in the freezer. Okay. Now freezers are normally about 3 to 5 degrees Celsius, but you can turn it down a little bit and get it to about 0 degrees Celsius. So let's put this can of beer in a freezer where the temperature is 0 and the heat transfer coefficient is equal to 10 watts per square meter degree Celsius. Okay, so this can of beer at 40 degrees Celsius, the question is how long will it take to get it to cool down to 10 degrees Celsius if we go and put it in the freezer. Again, in terms of the equation, if you can just show this again, Marilise, it's exactly the same equation that we've derived with the previous lecture, the one for the lumped system. That gives us the relationship between temperature and time, and that is the B value that is in the exponent. So if we now look at that exponent, we see that we need to calculate the surface area of that can of beer, and we need to get the volume. Okay, all the other stuff are known. So let's start with the surface area. What would the surface area be of that can of beer? Okay. It would be firstly, so let's divide it up into 3 problems. Firstly, we look at this outside area, which would be the big area. Okay. That would be equal to pi multiplied by the diameter. Pi multiplied by the diameter would be equal to the perimeter. Okay. Multiplied by the length. You agree? Okay. So the diameter we have is 60 moles. The length is 125 or 0.125 meters. So if we add that in there, then the surface area works out as 0.02922 square meters. I'm sure you don't want me to write it out for you. Okay. Pi multiplied by the diameter, 0.06, multiplied by L, 0.125 meters. So that's the surface area of the can of beer. Okay, sorry, that would now obviously be the outside surface, but then we need to add that, okay, plus this area, okay, and the same area on that side. Okay, so that would be 2 times, that area would be equal to pi divided by 4d squared. Okay. Sorry, and those 2 together, okay, let me rather write it like that, plus 2 times pi divided by 4 d squared. You all agree with me? Okay, is equal to that area that I've written down, 0.02922 square meters. So the surface area is this outside area of the beer can, plus that area, which is pi divided by 4d squared. And we've got that one and that one, so it's 2 of them. So that's the surface area of the can of beer. The volume would be equal to pi divided by 4d squared multiplied by the length. Okay, so this area, pi divided by 4d squared multiplied by the length. That is the volume of the can of beer. So that works out as 3.534 multiplied by 10 to the minus 4 square cubic meters. Right, now that we have that, we can go and calculate the B value. And the B value is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume, and Cp. Okay. The heat transfer coefficient is equal to 10. Okay, the surface area is equal to 0.02922 divided by the density of the beer. So we assume it is water, so it's 1,000, multiplied by the volume, which is equal to 3.534 multiplied by 10 to the minus 4 divided by the Cp value of the beer, which is 4179. And the result is that the B value works out as 1.978 multiplied by 10 to the minus 4 per second. Right, so let's get back to our original equation for a lumped system. That equation says that the temperature at a specific time t minus the environment temperature divided by the initial temperature minus the environment temperature is equal to, well, let's first maybe do the substitution. Okay, so we want to know how long will it take for the beer to cool down to 10 degrees. Okay? In an environment where the temperature is 0. The initial temperature of the beer is 40. And the environment temperature in the freezer is 0 degrees Celsius. Okay, and that would now be equal to E to the minus BT, and B is equal to 1.978 multiplied by 10 to the minus 4 multiplied by T. Okay, so in this equation, the only unknown is the time T. Right, so if we go and calculate the time t, who of you would like to guess how long will it take for a hot beer, putting it in the freezer, how long will it take to cool down to a good temperature of 10 degrees Celsius? Anybody? Nobody? How long? 40 minutes. Who said 40 minutes? You said 40 minutes, okay. So, if we work it out, it's 3504 seconds, which is 58 minutes. So it's almost an hour. So it's going to take a little bit longer. Okay. Now, the rugby is going to start in about half an hour. Or the soccer. So, now that you've done the calculation, as an engineering student with heat transfer, you need to think now of how can you make a plan? Okay, what can we do about it? Okay. So, what about, obviously, get it into an environment. So let's look at what drives this equation. Okay. What drives it, of course, is the B value. And in terms of the B value, the larger the B value, how quicker it will be. Okay. So in terms of making the B value larger, we need to, we cannot do anything about the surface area and the volume. Do you agree? With the volume, maybe you can drink half of the beer. That would help. Okay? But preferably not. You cannot do anything about the CP. You cannot do anything about the density. So what you can do something about is the heat transfer coefficient. Okay? So if you can get a first-year student getting into the fridge or something, running around with a beer, so that the heat transfer coefficient increases from 10 to 20, that would help. So that's part of the plan. Okay. Now the second plan is, if we look at this equation, is that this is very important. So we need to get it in a colder climate. So first year student, you go not into the freezer, you go into the fridge there at the supermarket. You're going to have to make a plan. And now that environment temperature drops to minus 20. Okay. And the heat transfer coefficient increases to 20 watts per square meter degrees Celsius. So the student is now running there around with the beer can in his hand. Okay. Now that would not really be a good thing to do. What you can do is you can put the beer in that area and put a fan over it. Okay. Because the fan would increase the heat transfer coefficient. Okay. So if we make those two adjustments, would you like to guess now how long it would take for the beer to decrease to 10 degrees Celsius?
40 minutes.
40 minutes. Okay. So, $29 minutes, still half an hour, for the beer to decrease in temperature from 40 degrees to 10 degrees. Right. Any questions on this problem? You all follow it? It's very simple and easy, isn't it? Okay. Something that we have to remember here, is that with this problem, which is a lump system problem, and that is the limitation of this approach, if we look at the temperature here on the surface, let's suppose it is 0.1, and there's 0.2, and there's 0.3. If we would go and plot the temperatures of them, they would all fall on top of each other. Okay. That is the limitation of the lump system approach. So, I've told you that we're going to do two examples, and then I'm going to come back to the value of B, because it's a very important value there. So, what is being used to help us, to guide us into making the decision if we should use the lump system approach or not is the following. Firstly, the definition of a characteristic length. And the characteristic length is the volume divided by the surface area. The characteristic length. Okay. You're going to see just now why that is important. Now that is being used in a number which is called the Biot number. And the Biot number, by definition, is the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity K. So that's a Biot number. Now, heat transfer, we're going to have many of these numbers. Now, this number, there's a definition of it, and what it says in the textbook is the lump system approach is valid, or it will give you good answers if the Biot number is smaller than 0.1. So you can go and test with a Biot number to determine if you can use this approach or not. Okay. Now, the thing is, that is all good and well, but the question is why? And that is why you as students also should ask yourself always, why? Okay. So why do you think must the Biot number be smaller than 0.1 and not smaller than 1? You guys? You guys? No, sorry, the two guys behind you, please. Why do you think should the Biot number be smaller than 0.1 and not smaller than 1?
Smaller numbers will be more correct.
Sorry?
The smaller numbers will be more accurate.
Okay, but why is this decision of 0.1 important? Okay. Yep.
The conductivity is very high. That means the temperature difference inside the cathode.
Good, you're on the right track, and I'm going to show it to you just now. So let's just look at these two examples first, and then I'm going to come back to the fundamental explanation. The first one is, let's look at the sphere. Okay. The sphere, and the other one was the beer. So if we look at the sphere, then the characteristic length is the volume divided by the surface area. If we go and do the calculation for the sphere, then the characteristic length is equal to 0.001667 meters. And if we do the same for the beer can, then it is equal to 0.0121 meters. Okay. If we go and calculate the Biot number, now for these two cases, which is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity. Okay. For the sphere, here's the heat transfer coefficient. Do you see? 12. And there's the thermal conductivity, 429. So if we do the substitution in here, the heat transfer coefficient multiplied by this characteristic length divided by that thermal conductivity, then the Biot number is equal to 4.7 multiplied by 10 to the minus 5. If we do the same for the beer can, with the beer, the heat transfer coefficient on the outside was 10. Okay, the thermal conductivity of the water is 0.631. So if we put it in the calculation for the Biot number, then the Biot number is equal to 0.1917. Okay, so this Biot number is not smaller than 1. So it tells us that in this case, we can use the lump system. But in this case, the lump system approach would not give us very accurate results. But still, it doesn't tell us why we should use 0.1. Where does it come from? Well, it comes from the fact that, and I hope you remember, that when you've looked at chapters 1 to 3 in your textbook of Cengel and Ghajar, you said that the heat transfer rate can be described as delta T divided by a resistance. Just like in electricity, the current is equal to the voltage difference divided by the resistance of the system. So like current flow, flow of heat transfer is exactly the same thing. It's an analogy. And then you've derived that for conduction heat transfer, that resistance is typically for a plane wall equal to L divided by Ka. And L was the thickness of the plate. Do you remember that? And then you've also done it for a sphere and for a cylinder. Then you've also derived that the convection heat transfer coefficient is equal to 1 divided by the heat transfer coefficient, 1 divided by the heat transfer coefficient multiplied by the area. And then the radiation one you also did. Let me just write it down for you. It is equal to 1 divided by the radiation heat transfer coefficient multiplied by the area, and this heat transfer coefficient is a little bit more complex to determine. But in principle, you can write all of them like that. Right, now let's look at the ratio of conduction resistance to convection. The ratio of conduction to convection. The conduction is equal to L divided by Ka. The convection is equal to 1 divided by the heat transfer coefficient multiplied by the area. And that is equal to the heat transfer coefficient multiplied by by L. Those two cancel out, divided by K. And if we compare that to that, we see it is the Biot number. So the Biot number, by definition, is the ratio of conduction resistance to convective resistance. Are you all happy with that, ladies and gentlemen? Now again, why 0.1? What was the reason for that selection? The reason for this selection, it was an arbitrary selection, and that is where you as engineers will have to make your judgment one day. So if we now just think of fundamentally the body that we want to consider, that was a body that we've derived for that equation. It could have any surface, any volume, etc. Okay, now this body will have a certain resistance which is determined by what? The resistance would be determined by the thermal conductivity and its geometry and length. You agree? And then on the outside there will be the convection. It would be the environment. So this is the ratio of convection to conduction. And for this specific case, where we've looked at the beer, the heat transfer rate was from the high temperature to the low temperature, and it was in that direction. And this is something that is going to come up in many cases in heat transfer, because we want to optimize systems, we want to get maximum heat transfer rate or minimum heat transfer rate. And it is very important that you critically look at the different terms, because with these types of problems you can normally have at least 3 types of categories. Okay. Now the first category of problem would be maybe where the thermal resistance inside the body would be massive, while the convection resistance is almost negligible. So the fundamental question is, what determines the heat transfer rate? What is the limitation? The limitation in this case would be inside the body. The resistance inside the body is high and the heat cannot get through. Okay. The opposite problem is a problem where the heat transfer rate, the resistance inside the body is small, but the resistance of the convection is extremely large. Okay. Or then categories of problems where the orders of magnitudes of these two are approximately the same. Okay. Now if you think about this carefully and you go and look at different problems, then the lumped system approach is valid for this one. Okay. So for all bodies who have a very small thermal resistance can be described very, very well by this approach. So this is the lumped one. Now just to give you an idea, I did go and calculate the resistances, and it's not, you don't have to go and do it, I did go and do it for these two cases. So for the steel sphere, okay, just on a scale, let's suppose this resistance, you can describe it as 1 millimeter in length. Okay? If that is 1, then this resistance here will be 21,245. So 1 millimeter to almost 21 kilometers, is that right? No, 21 meters. 21 meters. Just on scale. Okay. So the flow of heat through here, there's no resistance through it. And that is the reason why the lump system approach works very well. And it also says that in that body, there's almost not going to be any temperature differences. They're almost, all of them are going to be approximately the same. In the case of the beer, it works out as this one as 5.2 on the inside, and that one there is 1. Okay, 5 to 1. So where does the 0.1 come from? It comes from 1 to 10. But it is an arbitrary choice. Okay, so it's not a law. So there will be many cases where you're maybe close to this, where you can still use the lump system approach and get reasonable answers. The thing in general also that we need to look at is, I want to write down this equation. Yeah, let me write it down here. The Biot number is equal to the heat transfer coefficient, the length divided by K. So, as you've rightly said, the Biot number means it's the resistance of conduction to convection. And 10 is a thumb suck. Okay, 10 is a thumb suck. But in general, it means that the smaller the Biot number, the better the lump system will work. Okay. Small Biot means lumped system is great. It will work. That is what it means. What do we need to get the Biot number small? Firstly, we need a heat transfer coefficient that is low. Low heat transfer coefficients. So normally a body in air, typically air with natural convection, a natural convection environment, typically about 10, 20, maybe to 100. The moment you get to forced convection, then the heat transfer coefficient increases to hundreds to thousands, 10,000s. Okay, so the heat transfer coefficient must be low. The next thing is LC must be low. What does it mean? It means small bodies. Small bodies. Okay, so if L is low. And then thirdly, what would make this number also a small number? It would be when the thermal conductivity is high. Okay, so all geometries of bodies with a high thermal conductivity, copper, silver, all of them, would work well and contribute in getting the Biot number to a small number. This is a very important concept. You need to understand it very well, because you're going to be in a situation where you'll have to choose the solution methodology that you're going to use. And you will only be able to do it correctly if you understand these fundamentals very well. Don't just try to apply the equation. Ladies and gentlemen, thank you very much.